Okay, in the previous video, we modeled the height of a rider or one of these buckets here on the London Eye Ferris wheel. And we did this using circular functions, what trigonometry calls circular functions. But as mentioned, the plan is to, going forward for the rest of this course, we're going to put the idea of a circular function off to the side and instead just think about, if you want to model something circular motion or whatever, think about how you can just use trig functions to do that. However, before putting circular functions off to the side, I want to explain to you what the textbook means by this idea of a circular function, and then work one example problem showing how you would use circular functions. And that's what the previous video was about. And now the purpose of this video is I want to illustrate to you how what you would use circular functions for, you can do the exact same thing with regular trig functions. In fact, they're really the exact same thing. It's just more of circular functions are just viewing trig functions from another kind of perspective is all. So there's really no difference. And that's what we're going to illustrate here in this video. Okay, so what we're going to do here is, once again, we're going to come up with a function that gives the height of one of these buckets here all the way to the ground level. Okay, the diameter of the London Eye is a little less than 400 feet. Okay, and we'll say that the distance from the loading point to ground level we'll say is about 20 feet. And then the idea is the input that we have, so, you know, h as a function of what? As a function of time? Well, no, we're not thinking about time. We're just coming up with a hypothetical scenario where maybe there's like some computer screens here that the operator looks at, and for each bucket, and I don't know how, this is not that realistic. I don't know why you would need this. I'm just making up a hypothetical situation, but let's think about how the operator, that each one of the buckets has like a transducer that it sends a live reading giving a value of a percent value between 0 and 100% that represents its location along the diameter. So if the bucket is, you know, this bucket, the reading would be 14%. This bucket, the reading would be getting close to 50%. At 50%, you're at the highest point all the way, and then when you get to 100%, it goes back to 0. So there's like a live reading for each bucket, but we're going to focus on one bucket to get the height formula. But that's the input we have. We've got a live reading for the bucket that gives its percent location on the circle. You know, sensors like that have like insanely high frequencies. So, you know, it'll be giving that p-value to the computer screen like 1,000 times per second or something like that. You can think about. So it's like a live reading. If the Ferris wheel is moving, then you can see that p-value update almost instantaneously. And so what we're thinking about is we want to write like a code into the software that also gives the h value, the instantaneous h value. But all we have to work with is that p value. So let's come up with a formula for h as a function of this p using trig functions. So there is the Ferris wheel. And then we're saying that, let's say ground level is here. This distance is 20 feet. Here's the center of the circle. Okay, and the diameter is 400 feet. And let's just put, here's a bucket at some random position, and it has a height h. And it has a corresponding p-value, a height h and a p-value. That's the percent between 0 and 100 that represents this location on the Ferris wheel, where 0 is the boarding point and like 50 is the highest point. Okay, so how can we come up with a function for h as a function of p? Well, if we're going to use trig functions, it would be a good idea to put an xy coordinate system centered at the center point of the circle. You know, we could center it here maybe, we could center it down here. But trig functions in general, you can relate to circles. In particular, if you're using radians, it's really useful because of the way radians are defined. But you could still do it in degrees, but radians are useful. Make it easier to work with trig functions relating it to a circle. And in particular, the way that radians are related to a circle is when you have the coordinate system origin at the center of the circle. So let's put the origin of the coordinate system at the center of the Ferris wheel. Okay, it's XY coordinate system. Just to be clear, we could put the coordinate system here, the origin there, and it's not like we couldn't do anything with trig functions, but it would just be unnecessarily more complicated. We would still have to have this as our starting point. We'd have to go to the center of the Ferris wheel circle and kind of work from there. Every single calculation we come up with, we'd have to kind of start by shifting everything to the center here, then going from there. So why would we do that? You might say, well, when would you ever have to do that? Well, I don't know. Maybe it's like a more complicated system where you've got multiple circles, you know, so you kind of put this at the kind of the center point of all of the circles, something like that. But okay, we've only got one Ferris wheel here, so we're going to put the origin at the center of the Ferris wheel. And let me go ahead and move this 20-foot onto the y-axis. It kind of makes it look confusing. So this is 20 feet. Okay, now as before, let's go ahead and call this x prime and y prime. We might not have to, this might not be necessary, but it might be the case that I don't want to confuse the coordinates here with the outputs of the trig functions. Okay, but with that, the point P has a x coordinate and a y coordinate. In this case, x prime would be negative, y prime would be positive. And the goal is with P, well, this is not the point, I'm sorry, this is not the point P. P is the parameter. So, yeah, I'm saying that wrong. This is not point P. P is the parameter we have associated with this point. But we want to relate, the goal is we want to, given an input P, we want to find what y prime is. And once you have y prime, you could get h. Okay, so we have multiple options on how we can approach getting the y prime given this input P. We could think about the corresponding, for any position of the bucket, you could think about the corresponding right triangle that's created. You could create this right triangle in any quadrant, and with that percentage, we could figure out what this angle is, and then use the trig functions to get y prime. That's one way. Or there's another way we could do it, and I want to do it the other way because it's more parallel to what we did with the circular functions, and I'm trying to compare the method of circular functions and trig functions. We can think about what is the arc length that the bucket has traced out relative to the full arc length. So the full circle arc length is 2 pi times the radius is 200. So it's 400 pi feet. In the previous video, we called this S prime, and S prime was measured from, S prime is equal to 0, and you go all the way around to S prime is equal to 400 pi. Okay, well, let's do the exact same thing here. It would be, with your knowledge of trig functions, it would be really easy to just make this be S prime is equal to 0. Or we could call it S now because we're not using the circular functions with the input as S. We could just call it S now. So it would be simple to just make this S equal to 0. However, we could have done the same thing with the circular functions. It was a little more confusing with because we weren't as familiar with circular functions. So in that case, let's just go ahead and make this, to make this parallel to what we did in the previous video, let's make this the 0 position. So the bucket here at any moment in time has its associated with it is this arc length. And we'll just call that S. We don't need to say S prime again because we're not inputting any S into the trig functions. Okay, so what is S? If we know what P is, then what's S? Well, that's exactly what S prime was. P, the 0 point of P is down here. And so I'll explain it again, how we figured this out. So if we imagine that, hypothetically, let's say that P was 0 here. Okay, so again, just so you understand what P is 0 down here, then here it would be 25%, then here 50%, then 75, then 100. It would go back to 0 once you get to 100. Let's put P as being 0 here. So here P would be, so here, when the bucket's here, P would be approaching 50%. Maybe it's like 42% right here. So if we imagine that the same starting point, then S is easy because you've got the full circumference, 400 pi, but then you just multiply that by the percent. What percent of the full circumference is the location, right? Here it's like 42%. So you take 42% of the full circumference. Okay, but they're not at the same starting point. P is like shifted back 25% of a rotation, a quarter of a rotation. And so we can think about, we need to shift P here. And what we're going to do is if we think, okay, when S is equal to 0, what is P? When S is 0, what is P? P is 25%. So that means, okay, you have 400 pi, and we need to shift P, something is equal to 0. So what do we need to shift? When S is equal to 0, that means that we need this. Right? So here, when P is 0.25, this equals 0. So that's the formula relating S and P. Right? So when P is equal to 0, S is negative a quarter of a turn. And that's correct. When P is equal to 75%, that's here, that should be 50% of a full rotation. If S is 0 here, and that's what you get. 0.75 minus 0.25 is 0.5. So there's the formula relating S and P. Okay, so how do we go from here? We have S. How can we go from S to getting Y prime? Well, let's just think in terms of radians. You know, we could think in terms of degrees and do the same thing, but, you know, when you're dealing with arc lengths on a circle, that's like the definition of radians, so why not work in radians? Okay, and we can, you know, we didn't really allow ourselves to think about angles and triangles much at all with the circular functions, but with the trig functions, let's absolutely think about angles if it helps. So any arc length S subtends an angle theta. Okay, and if theta is in radians, we can easily get theta if we have the arc length. It's just S divided by R, where R in this case is 200. So S divided by 200 is, so we've got 400 pi. So this is divided by 200. This is going to be 2 pi. And that's theta. That's the arc, the angle that the S subtends. That's theta. So which again is S over 200. Okay, now you might be thinking that the next step is we need to get this reference angle. But actually, no, we don't. We can just it would be better to just go ahead and take the trig functions of this angle directly. And why is that? Because if we do that, then we'll get the correct sign of y prime. That's the advantage of doing, like this is like the definition of trig functions. If we take the trig functions of this angle, it's the exact same as the trig functions of the reference angle, but it honors the sign of y prime or x prime, and that's what we want. We want to know if y prime is negative or positive. So, okay, that's perfect. So sine of theta is what? So this is 200. It's opposite, come to the reference angle, opposite over hypotenuse. But we come to the reference angle, but we're actually doing this angle because if y prime could be negative or positive. So it's really, it's this angle we're evaluating the trig functions of. So opposite over hypotenuse. And there you go. There is y prime. Okay, now you see how this applies for any arc length S? It's going to give us y prime if the arc length is less than half of a rotation. It's going to give us a positive y prime, which makes sense. If it's more than half of a rotation, or between half of a rotation and a full rotation, it's going to give us a negative y prime. That's what we want. Okay, so now how do we relate y prime to h? Well, so all it's going to be is we're going to say that, okay, it's kind of confusing looking, but this is h. This entire distance is h. So what we want to do is we want to add this distance, so 200 plus 20 plus y prime. That's going to be h. So h is 200 plus 20 plus y prime. And if y prime is negative, then you end up subtracting y prime, which is what you want. In this case, we want to add the y prime, but but the formula works even if y prime is negative because it subtracts the y prime, which makes sense, right? If the bucket was here, then you would want to do 200 plus 20 minus this distance, but that would be y prime, and that would give you h. So that's y prime plus 220. Okay, so there's all the formulas. Let's put everything together into one formula. So, okay, y prime is 200 sine theta, so let's substitute y prime here. So h is equal to 200 sine theta plus 220. Okay, but theta is 2 pi times p minus 0.25. So and there you go. Into the software, you have a p-value for the passenger or a bucket. You put it through this formula with we're thinking about this as a trig function. You put it into this formula, and you put sine in radian mode. You put your trig function in radian mode, put it into this formula, and you get h.